Hello everyone, I would like to begin by expressing our appreciation for this platform by the conference organizers to share our work in this video presentation. The topic of this presentation is Catalytic Effect of Metal-Loaded SBA-15 on Naphthalene Methylation with Methanol to produce Methylnaphthalenes and di-methylnaphthalenes. My name is Abdulaziz Abdullah, a master's student at Ankara University Department of Chemical Engineering, and I will be presenting this work on behalf of the authors. The content of this presentation will include the aims of the study, a brief introduction and background, then I will share the experimental procedures carried out in the study. Afterwards, I will discuss the results of these experiments, and finally, we will understand and conclude on some key points and takeaways from this work. A look at the aims and objectives of the study. To begin with, this research was carried out primarily with the aim of evaluating the catalytic activity of platinum incorporated onto mesoporous SBA-15 in the methylation of naphthalene. Specifically, we set out to investigate the selectivity of these catalysts for 2,6-di-methylnaphthalenes, the yield of methylnaphthalenes, and also the conversion of naphthalene in the methylation reaction. Let's begin with a brief background introduction to understand the relevance of this work. Plastics as polymers are an integral part of engineering and society. Polyethylene terephthalate is one of the most important commercial engineering polyester thermoplastics. With good thermal and mechanical properties, it has varied applications in our daily lives, such as use for packages and fibers. A novel superior alternative to polyethylene terephthalate is polyethylene naphthalate, which exhibits superior tensile strength, barrier properties, and high stability. This material outperforms polyethylene terephthalate in engineering applications, and then there is a growing demand for it industrially. The most common route for the synthesis of polyethylene naphthalate involves primarily the oxidation of a dialkyl naphthalene to a dicarboxylic acid, its esterification to dimethylnaphthalene dicarboxylate, and then finally copolymerization with ethylene glycol to produce polyethylene naphthalate. In this route, a key material is the dialkyl naphthalene, which is produced from a naphthalene source. 2,6-dimethylnaphthalene is the most preferred. However, its high cost and low availability limits the large-scale production and commercialization of polyethylene naphthalate. Consequently, the focus of several research has been the selective synthesis of 2,6-dimethylnaphthalene and methyl-naphthalenes. Methylation of low-value naphthalene to 2,6-dimethylnaphthalene and methyl-naphthalenes is one of the efficient methods which has been proposed. Heterogeneous catalysts, specifically zeolites, with their varied structure, pore size, and acidity have been widely applied in this area. Even though zeolites such as ZSM5 possess high selectivity for 2,6-dimethylnaphthalenes, the conversion of reactants and yield is low due to the diffusion constraint of larger molecules within the zeolite pores. As a result, mesoporous materials which have uniform pore sizes between 2 to 50 nanometers have recently drawn interest for application in catalysis. SBA-15 with its hexagonal channels, large surface area, and tunable pore sizes has been used in reactions such as oxidation, hydrogenation, etc. with interesting results. Despite SBA-15 being employed in several catalytic transformations, this is the foremost investigation for its application in the methylation of naphthalene. Now a look at the experimental study. In the catalyst preparations, SBA-15 was prepared following a synthesis route as reported in literature. To this effect, SBA-15 was synthesized hydrothermally at 85 degrees Celsius for 24 hours using pluronic 1,2,3 in an acidic medium and tetraethyl autosilicate as a silicate source. The metal loading was also achieved by a wet impregnation of platinum precursor. In this method, SBA-15 was dissolved in a chloroplatinic acid solution and then kept for 24 hours. Subsequently, the material was dried and calcined for 6 hours at 550 degrees Celsius to obtain platinum-loaded SBA-15 as shown in the figure. Characterization of the prepared catalyst were done using XRD, XRF, and BET techniques. The experimental setup of the study is as shown below. Methylation of naphthalene was performed at atmospheric pressure in a fixed bed reactor which consisted of a catalytic bed, a PID temperature controller connected to a heating source. The feed, consisting of 1:3 to 10 molar ratio of naphthalene, methanol, and 1,2,4-trimethylbenzene as solvent, was supplied using a high-pressure pump. For the tests, 2 cm³ of catalyst pellets were placed in the reactor and initially activated in a nitrogen flow at 500 degrees Celsius. Subsequently, the reactions were then carried out at temperatures of 400 to 500 degrees Celsius and with Hawley space velocity of 2 to 3 per hour. The reaction products were condensed and analyzed in a gas chromatograph connected to a mass spectrometer. Moving on to the results. Firstly, the characterization of the catalysts, as mentioned earlier, were done using XRD, XRF, and BET analysis. From the nitrogen sorption isotherms as shown, it is seen that both SBA-15 and PT-SBA-15 catalysts show monolayer and multilayer H1 hysteresis type 4 adsorption trends typical of mesoporous materials. However, the low and almost parallel inflection on the platinum SBA-15 isotherm, in contrast to the SBA-15, is as a result of the alteration of textural properties due to the impregnation of metal platinum. From the table, we can confirm this change as we see the narrowing of pore volume, pore diameter, and reduction in surface area. These differences will reflect to a significant effect in the methylation reaction. In addition, the elemental compositions from XRF as well as XRD peaks at 2 theta, 39.6 degrees, 44 degrees, 64.3 degrees, and 77.4 degrees confirm the successful incorporation of platinum onto SBA-15. Peaks analysis using expert high-score software and ICSD database correspond to reference patterns of platinum as seen on the XRD diagram. To discuss the activity and effect of platinum loading on the catalyst, the naphthalene conversion, 2,6-tri-di-methylnaphthalene selectivity, as well as methylnaphthalene yields were evaluated. From the conversions as shown in the graphs, the naphthalene conversion on SBA-15 is typically high. This could be linked to the large surface area and wide pore structure. Consequently, the highest conversion of 97% was recorded at 450 degrees Celsius. On the other hand, conversion decreased with increasing temperature on PT-SBA-15 due to the contraction of textural properties. However, a high conversion of 85.2% was still achieved. Furthermore, although methylnaphthalenes and di-methylnaphthalenes were not identified in methylation products on SBA-15 catalysts, in contrast, PT-SBA-15 showed significant selectivity for 2,6-tri-di-methylnaphthalene isomers across all temperatures tested. The highest selectivity of 25.8% was achieved at 450 degrees Celsius and a space velocity of 2 per hour. In addition to high selectivity for 2,6-tri-di-methylnaphthalenes, PT-loaded catalysts showed high yield for methylnaphthalenes at higher temperatures. As mentioned previously, methylnaphthalenes are also important starting materials for 2,6-dimethylnaphthalene synthesis. As can be seen in the product distribution on PT-SBA-15 at 500 degrees Celsius on the right, 68.1% of methylnaphthalenes as product is achieved. Furthermore, the more desirable 2-methylnaphthalene isomer is produced in contrast to 1-methylnaphthalene. The distribution also shows high amount of dialkylated products compared to undesirable tri- and tetraalkylated naphthalenes. To further evaluate the selectivity towards 2,6-dimethylnaphthalene and 2-methylnaphthalene products, the ratio to undesirable 2,7-dimethylnaphthalene and 1-methylnaphthalene were evaluated. It can be seen that across all temperatures and particularly at high residence times, the ratio of 2,6 to 2,7-dimethylnaphthalene and 2 to 1-methylnaphthalene remains above the thermodynamical value of 1. This further supports the fact that the PT-SBA-15 catalyst favors the beta position on naphthalene and formation of desirable methylation products. In conclusion, at the end of the study, it was confirmed that the prepared catalyst corresponds to the mesoporous class of materials, and also the impregnation of platinum affected the textural properties to the enhancement of catalytic activity of SBA-15. Moreover, the wider pores of SBA-15 facilitate easy diffusion of reactant, which is reflected by high conversion, even though methyl naphthalene and dimethyl naphthalene products were not produced. The incorporation of platinum, which affected textural properties, also improved the catalytic activity. High conversion, yield of methyl naphthalenes, and selectivity of 2,6-dimethyl naphthalenes were achieved. Furthermore, at low residence times, platinum SBA-15 catalyst favors the formation of desirable 2-methyl naphthalene and 2,6-dimethyl naphthalenes. For further study, it is proposed that a selective medium pore zeolite such as ZSM5 could be combined with metal-loaded SBA-15 for improved activity. This is a list of references used in this work. Finally, we would like to extend our foremost gratitude to the Eurasian Conference organizers for this platform to share our research, and to you, the audience, for your interest in our work. Thank you.